All right, good morning. In this video lecture, we're going to talk about curved surfaces in the hydrostatic force and how we calculate that. And we'll do a practice problem. Okay, so if we have a body of water like this, and this is water, and down below, this is a curved section here, and all we do is we pretty much just take the curved section, make a dotted line or whatever, and what we're going to do is we just take that section and we analyze it. Okay, so we're going to do a free body diagram on this. So if I redraw this shape, okay, you know, it kind of goes back like this, right? Okay. And what we need to do is basically this surface, we'll calculate a force. We'll calculate a force over here. And then the back side, so like if we do a dotted, something like that, it's going to be kind of tricky. But basically this force acting up here, like against this. Okay, and that's your curved surfaces. This is FR. Okay, so the way I would do this is, let me just back up a few. And we'll just look at a 2D image. Oh, that's as far as I can go. Okay, I'll erase it. Okay. So what we're going to do is this creates a force perpendicular, right? And then this is basically creates a force, and it's more to the bottom because of pressure with depth. That's why this one is all the way horizontally perfect, because it's at one height. And then this one kind of starts small and then eventually gets bigger, right? And then it stays the same because pressure with depth. And all of these lines are perpendicular to the red, okay? So this is going to be what we'll call Fy, acting down. We'll call this one Fx. And then over here, somewhere, this is Fr. And we can split this up into FH and to FV. And you could have, or you pretty much do, you have a weight of the water, right? It's pretty much every side of that shape, okay, is what we're going to do. And we're going to use, and then you just sum the forces in the Y, set it to 0, and then sum the forces in the X and set it to 0. Okay? So let's do a practice problem so you know what you're doing here. Okay. All right. The water side of a wall of a 70-meter long dam is a quarter circle with a radius of 7 meters. Determine the hydrostatic force on the dam and its line of action when the dam is filled to the rim. All right, so let's just, we'll write some given. W, 70 meters. R is 7 meters. Density of water is 1,000 kilograms per meter cubed. G is 9.81 meters per second squared. H is equal to R, and that's equal to 7 meters. Don't really understand those givens without a sketch, right? So here is this, and then we got a radius right here. Okay. So basically this is H, this is R. Okay. So this is basically filled with water. Okay. We're looking for F of R. All right. Now I'm going to do a free body diagram. Let's see if I can do this. FBD. And we're only going to look at the curved section. Okay. So it's like this. Goes over. Curve. And I'm going to try to do it in 3D. That goes over like that. Okay. And then like this. And it goes back like that. And that connects. Okay. So this is just this curved section that we just kind of take out. And it's the free body diagram of the water. All right. So what we're going to have is right here. Actually, that acts down a little bit down farther, right? Because it's 2/3. This is f of x. This top surface, which I'll kind of make like a light red, that is f of y. We have the weight of that. And then we have this hydrostatic force, which we can break up into components. F of H and F of V. Okay, vertical, horizontal. All right. And just to completeness, the orange is that left surface. So we're doing a free body diagram on all of those surfaces. All right. So let's write this solution, and it would be Newton's second law. And we're going to sum the forces in the x, set it equal to 0. We'll make to the right positive. And then we'll sum forces in the y, set that equals 0, and make up positive. And these are all static, so everything's 0. So in the x, we have f of x minus f of horizontal equals 0. In the y, we have minus fy minus w plus fv equals 0. So the horizontal is equal to f of x, and the vertical would be f of y plus w. Okay, cool. I'll just change the color here. Oops. All right. So f of h and f of x, which is the horizontal, if you remember, is p average in the x direction times a. And that equals, I'll just put p average x, and the area is h times w. Okay, so h is the height. I don't know why it's doing that. From here down to here, right? And then w is from here. That's the width in and out of the page. Okay, and then I'm going to do it here because I think that's what's causing that to highlight. P average is rho GHC times H times W. And F of H would be rho G H over 2 times H times W. Okay. And so we can plug this in. F of H, density is 1,000 kilograms per meter cubed times 9.81 meters per second squared times 7 meters over 2 times 7 meters times 70 meters. So the horizontal component what do we have? 1.68 times 10 to the 7 newtons. So that's the horizontal component. All right. Now let's go to the y direction. And sorry, I'm going to do it right here so it doesn't highlight that. And I'll do it in purple. F of v, the y component would be P average y times area and plus W. And the weight we'll put is mg for right now. Okay. So FV, P average in the y. So P average. So this is the top. This is right here at the top. Okay. And we're dealing with hydrostatic forces. If it's at the top, there's the atmospheric, we use gauge and it's 0. Now, if this was below the water, like in my thing here, then you would have to calculate this distance, right, from here down to here to find an average pressure. But because we're at the surface, it's atmospheric, that goes to 0. So this is just m times g. Okay. So now the mass of this, we actually have to break out and times it by density and volume times gravity. Okay, gravity and g we know. Now the volume, okay, is this. It's it's going to be, if you remember, if you take a cylinder, okay, then it would be pi r squared times the length. Well, because we got a quarter, then it would be pi r squared over 4 times the width. All right, so now we can plug this in. 1,000 kilograms per meter cubed times 9.81 meters per second squared times pi over 4 times the radius, which is 7 meters squared, times 70 meters. And I'm going to make sure I didn't miss anything. 1,000, 921, 70 pi. Yep. So F of V, the vertical, is 2.64 times 10 to the 7 newtons. Okay. And then to find FR, just take the square root of FH squared plus FV squared. So FR becomes 1.68 times 10 to the 7 newtons squared plus 2.64 times 10 to the 7 newtons squared. I should put probably parentheses around those. FR is now 3.13 times 10 to the 7 newtons. We'll box our answer. And then if we want to find the angle, so the angle that it acts at, be tan theta of FV over FH. Theta is tan to the minus 1 of basically FV over FH. So theta tan to the minus 1 is 2.64 times 10 to the 7 newtons over 1.68 times 10 to the 7 newtons. And we get theta to be 57.5 degrees. Okay. Which, if I go back up here, that is right here. That is theta. Okay. Now, you don't have to draw that perfectly. What you could do is in AutoCAD or another drawing program, draw an angle, draw a line at 57.5 and then figure out where it's perpendicular to that curve. And that's where it would act. So, but this is how you do and analyze curved surfaces for hydrostatic forces. Thank you. If you have questions, let me know.